I also appreciate the fact that tonight there is a football game on, which I know that all of you are missing. So that's a tough competition in this town, I believe. So today I'm going to talk about the observational evidence for dark energy. And this talk will have some, it's sort of designed for the chemists and physicists in the audience. There will be material for astronomers, but I will attempt to keep it so that everyone has a basic idea of what I'm doing. If you don't understand what I'm saying, look confused, and I will answer or continue with more explanation. So, I think it's important to understand the cosmological constant or dark energy in the context of history because it has a long history. The birth of modern cosmological theory happened in 1915 with the publishing by Einstein and Hilbert of the equations of general relativity. And that is the foundations of the theory which we use to explain the universe. In 1916, Einstein published in 1916, the first cosmological model was published here by De Sitter, who was in Leiden, a model of an empty universe, a universe that had nothing in it. And Einstein was fairly, he thought that was a stupid universe to do anything. It was a trivial universe and not worth studying. But Einstein then looked at universes that had matter in them in 1917, and he realized soon that such a universe would be in motion, and so he added a term to his equations, which he called the cosmological constant, and this term made gravity repulse itself and put the universe, he thought, into balance so it would be neither expanding nor contracting. And that cosmological constant Einstein held on to until about 1931. In 1922, the modern interpretation of our understanding of the universe was published by Freedman in Russia for a universe that was homogeneous and isotropic. So homogeneous means it's the same everywhere, and isotropic means it has no preferred direction. And those are the simplest universes you can think of, but they also are universes that seem to represent the universe we live in. So in 1916, we had the birth of observational cosmology, not theory, but the observations. In 1916, Vesto Slipher found the redshifts of galaxies, the fact that galaxies' light was shifted to the reds, their spectra were stretched. They didn't know why. It was stretched by the expanding universe is what it turned out. In 1923, Hubble realized that galaxies were actually beyond the Milky Way, that a galaxy is what we know today, a collection of stars, island little universes in the sky. In 1927, a Belgian monk, Lemaitre, published part of his thesis called A Homogeneous Universe of Constant Mass and Growing Radius. And in this work, he independently derived these equations which we use to describe the universe. It's being homogeneous and isotropic, because he didn't know about the Russians' publication. He suggested that the universe was expanding, and he actually went and used Hubble's and Slipher's data to show the effect happened in nature. So Lemaitre really deserves, in my opinion, credit for discovering the expansion of the universe. But I don't think Lemaitre was a terribly popular man back there. He was seen as a bit of an eccentric, and his work was actually reviewed by Einstein, and Einstein said that the mathematics seemed correct, but his ideas were fanciful. Hubble didn't ask Einstein. Hubble instead published his work in the U.S., in the National Academy of the U.S., and then did a press release. And essentially, that's where the expanding universe came along. By the 1930s, the basic paradigm that we use to describe the universe was in place. It's the same set of equations we use today. The universe we treat as being very simple because, fortunately, it appears to be so. We had the theory of gravity, general relativity, and the assumption of this homogeneous and isotropic universe. So for the physicists in the audience, but I think everyone can understand this, the homogeneous and isotropic universe has nothing to do with general relativity. It is geometry, and it's described by this equation, which connects time and space together. The idea is that if you have coordinates in a universe, which in this are like the radius r and the angle theta, I've gotten rid of one of the angles to make it simple, you have to worry about this factor, which turns out to be what we call the scale factor. It describes how the universe changes in size over time. So this factor A is sort of the relative size of the universe over time. And the equation here says that if I'm going to connect information in the universe, I have to worry about time. I have to worry about if the universe is getting bigger or smaller. And then I have my coordinate, and it turns out I have some geometry here. That term is whether or not the universe has curvature or not. And so in addition to that, we have general relativity. And general relativity gives you an equation to describe the universe, a differential equation, quite simple. And one of the things I'm going to refer to throughout the talk is a factor called omega. Omega is a description, it has no units. It is the ratio of how much matter there is in anything, for example, atoms or gravitational matter, compared to a critical density. And this critical density is the density that tells you whether or not space has curvature or not. Because in relativity, general relativity, if you have a universe which is heavy, has lots of stuff in it, it has curvature, it curves onto itself. If it has a moderate amount of material, so that's a heavy universe. If it has very little material, in relativity, space curves away from itself. And if it has just the right amount of material, it's flat. Okay, and you have to worry in general relativity about this curvature. All right, so with this dynamics, the dynamics of the universe, when you solve the Freedman equation, I'm going to do it simple for the non-astronomers in the audience. Over time, you have a universe which, if it is empty, it essentially just expands on a nice straight line. Of course, if the universe has a lot of stuff in it, it will expand and slow down over time, where the gravity in the universe, when you solve that differential equation, will slow the universe down over time. And if the universe had a cosmological constant in it, that pushes against the universe, and that actually speeds the universe up over time. Now, astronomers always like to make lavish predictions of the future, and so these models of the universe have different futures, which is interesting. A universe which has nothing in it keeps getting bigger and bigger over time. A universe which has a cosmological constant exponentially expands and gets, well, sort of to infinity quicker, but it expands very quickly over time. And a universe which has got a lot of matter in it, gravity in it, will eventually reach a maximum size and collapse down into what we would call the opposite of the Big Bang. So, now let's get to some of the details of the physics. It turns out when we look at stuff in the universe, we have to describe its physical properties. And its physical properties are described by what we say is the equation of state. This is how the matter behaves in the expanding universe. All right? And the basic idea is that the equation of state, the first order, is how the gravitational pressure is divided by its density. That doesn't mean much to most people. The easiest way to do is to figure out how the density behaves as space gets larger. And the equation of state essentially says is if the volume changes at this rate, if the density changes by the volume to this power, then the equation of state has this form. So this is best done by example. The equation of state for normal matter, we say it has zero pressure, zero gravitational pressure. The equation of state is zero because the density goes, as the universe expands, inversely with the volume. And so, for example, you can imagine if I take a piece of space and I have a single atom in it, and I double the volume, well, naturally the density halves. And you say, okay, what wouldn't behave like that? Well, something that has a different equation of state. So I have, here's an atom in a box, very simple. But a photon is different. The photon, when it's in the box, gets stretched. Its wavelength gets stretched. Its energy, therefore, drops. And it drops by the 1/3 power of the volume. So the density of a photon goes as rho to the -4/3, and so it has an equation of state here of 1/3. The cosmological constant, turns out, is energy density, which is tied to space itself. As the universe expands, the density in the cosmological constant stays constant. That's why we call it the cosmological constant. And so it has, according to this equation of state of -1. And so this is important because when we solve the differential equations for general relativity, it has a profound effect on the expansion of the universe. So I don't expect people to understand this in detail, but it's worthwhile just to see how easy and simple the universe is. The Freedman equation for a flat universe I can write as a very simple differential equation. And then I could put in the equation of state, which effectively is this. It says here that the density, when the universe goes up by a factor of 3, the density follows. Essentially, the density over the current density goes as the 3rd power of the scale length of the universe. I don't think that's any better than mine, is it?
Oh, you have one.
Yeah. So that's the equation of state. And you get a differential equation you can solve for a universe that has this equation of state. And that tells you that the universe expands, so the length scale in the universe expands as t to the 2/3 power. If instead the universe is full of photons, like we think it was when it was very young, then this equation of state, you have to go as the 4th power of the scale of the universe, and the solution goes as t to the half. So the universe expands differently. And finally, if you have a cosmological constant, then the density is independent of the scale length of the universe, and the differential equation, when you solve it, is an exponential expansion. Now, we can put this together with the idea that the amount of material in the universe is going to, what part species of matter is dominating the universe is going to change back in time, because the amount of density in radiation, for example, as I go back in time and the universe is compressing, then the amount of energy in the photons is going up as the scale length of the universe to the 4th power. All right? Whereas matter is going, I'm compressing the universe, then I change the scale by a factor of 2, the volume's a factor of 8, so that's the 3rd power, where the cosmological constant doesn't change at all. And so that means that the ratio of material, of what's in charge in the universe, changes back in time, essentially such that you could expect that the cosmological constant rapidly, if it exists now, will rapidly be inconsequential in the past, unless it is just overwhelmingly dominant. And eventually, if there are any photons in the universe, and there are a lot of photons in the universe, photons will eventually dominate over matter. So if you go back and look at a life history of our universe, I have the log of time here. I have the log of the scale length of the universe, of what I'm tracking a piece of part of the universe is. The universe, when it was young, had lots of photons. It was dominated by photons. It expanded as t to the half. At some point, the density in photons, dropping as the scale to the 4th power, gets overtaken by matter. And then when it's overtaken by matter, the universe expands as t to the 2/3 power. And then the cosmological constant, which is just sitting there invariant, the matter gets diluted more and more by the expansion, and eventually the cosmological constant takes over, and we have exponential expansion. All right, so that's sort of that's the intense part of the talk for the non-physicists in the audience. To test this set of matter, well, I should say I've got another equation set coming up here, but there are classical ways to test this. One thing you can do is you can go out and measure distances in the universe. So you can compare how bright an object appears at different amounts that the universe has stretched. So I can compare if how bright, for example, a star is whose light by the expanding universe has been stretched by a factor of 2 versus a factor of 3. And that depends on what is in the universe, as I'll show you. The other distance you can measure is not how bright something appears, but how big a rod appears. So for example, I have a rod like this. The further away you are in this room, the smaller that rod appears. That's what we call an angular size distance. Now, the universe is a funny place. Because the universe is expanding, it turns out that when you go back further and further in time, a rod like this gets smaller and smaller to a point, but eventually the rod starts getting bigger, appearing bigger again. And that's because photons are traveling on curved paths in our universe due to not just the geometry of the universe, but also due to the expansion of the universe. So from an equation point of view, this is a complicated equation, and I'm not going to spend much time on it. I just want to show you that there are equations that we do. We are fairly serious about what we do. The important part about this equation, so this equation tells you how bright an object appears in the sky. It looks complicated, and I'll show you what it really looks like graphically, but it's not as complicated as you think. The character Z here is the redshift. That tells you how much light has been stretched. So if light has been stretched by 100%, then Z is 1. If it's been stretched by 10%, it's a tenth. So the way we keep track of things in the universe is by how much their light has been stretched. We have to worry about the curvature of the universe, and this essentially tells you how much stuff. Kappa tells you the sum of all types of matter in the universe. It tells you whether or not the universe is curved onto itself, away from itself, or it's flat. The other thing we have to worry about is the omegas of the universe. How much stuff there is in the universe relative to the amount of material at critical density which makes the universe have zero curvature. And for each one of those types of matter, we have to worry about the equation of state. That's the only thing that matters for measuring distances in the universe, is how much stuff and what's its equation of state. So I'm going to show you a graph here that essentially plots what distances in the universe look like depending what's on the universe. So I'm going to set as my baseline here a universe that has nothing in it. That's the de Sitter universe I described in 1916. It's the trivial universe. A universe that has a lot of matter in it, that is, has a universe which has a critical density, it's flat, and has all of that in normal matter. Well, these objects are about 150% brighter compared to the trivial universe at a redshift of around 2.5 or 2. Of course, the further away you get, the bigger the effect is relative to the trivial universe. A universe that has 30% of that amount of matter, the objects behave, the distances behave very similarly, but the effect is not as pronounced. And so you can imagine by looking at distances and comparing near and far objects and how bright they appear, the objects, if the universe is very dense, the objects appear brighter compared to a universe that is less dense. And you can weigh the universe by just seeing how bright objects appear as a function of redshift. Nice, simple test. Things get complicated if you want to add other species of matter. For example, if you wanted to add a cosmological constant, for example, a 30%, 70% mix of a cosmological constant, then these objects appear fainter at low redshift nearby, but then they become brighter relative to our empty universe as a function of time. It's a very specific curve, and so again, by comparing our observations, we're going to try to make a measurement of distance as a function of redshift, and we're going to compare it to this family of curves that, remember, depend on how much stuff and what its equation of state is. Now, it turns out that how old the universe is depends on what the universe is made up of and its equation of state again. So this is a diagram that shows the total amount of matter, including the cosmological constant, for example, as a function of what the matter content of the universe is. So universes that have no cosmological constant follow this black line, and then these curves tell you what fraction, essentially how old the universe is relative to the Hubble constant. The inverse of the Hubble constant gives you the age of the universe. We think the Hubble constant is about 72, 73 kilometers per second per megaparsec, which gives an age of the universe of 14 billion years. And so this universe, for example, right here, the contour is 2/3, and so a universe which has omega matter equal 1, the age of the universe is 2/3 the age given by the Hubble constant. Now, the measurements from 1950 to 1990, people tried very hard to do this measurement, but the Hubble constant measurements were very difficult. These are measurements I did for my thesis, and I got a value of 73 plus or minus 7 for my thesis, which is looking very good given the current measurements. I'm not sure if people believed me at the time, but it is nice to at least have the right answer after the fact. And so given our understanding of the universe, of how old the universe is based on the oldest stars in the universe, which people thought were between 13 and 20 billion years back then it turned out in this, almost the entire diagram was filled. You couldn't make any progress. It was, the information just was not good enough. Now, in the 1970s and 1980s, a little wrinkle came into my standard model of the universe. We could explain distances using those equations, and we still use those, but we had to add a few extra ingredients to explain other measurements we had made of the universe, such as the cosmic microwave background. So the first of these ingredients was inflation, and inflation is essentially adding a time to the universe where the universe expanded by 60 orders of magnitude in the first instant that the universe was born, and this gives you a nice uniform cosmic microwave background, and it turns out it gives you the seeds of the formation of galaxies and structure in the universe today, because it magnifies the quantum fluctuations in the early universe. This process takes things which are 20 orders of magnitude smaller than an atom and blows them up to the size of the universe today. And so that causes quantum fluctuations, virtual particles being created. Those suddenly get separated and they become real fluctuations. And it gives you the things that become the galaxies of today. Now that sounds a little crazy, and it is a little crazy, but it does provide it more or less is the way that we explain the universe today, and it's more or less predicted a few things, all of which have come out to more or less be correct. But it is a cartoon model. It essentially is a way of giving you the initial conditions of the universe that make sense. If you don't do this, you would expect maybe the cosmic microwave background to be have temperatures all over the place. And if you don't create the seeds of structure by some method, you end up with the galaxies never forming. The universe would have started off too smooth or too lumpy, I don't know, but it wouldn't have started out the way it did. And so that's why this is an important ingredient. The other thing we had to add was something called cold dark matter, because it became very clear by looking at galaxies that about 85% of galaxy gravity was not in the form of stars or gas or anything we could identify with atoms. And so, in order to understand galaxies and the structure formation, that is the large-scale formation of galaxies, we needed to invent something that was not atomic matter, or what we call baryonic matter. It had to be something else that did not interact with itself or anything else in the universe except for via gravity. And that's called cold dark matter. And these things together sort of are the added parts of our model. And it turns out inflation predicts that the universe should be perfectly flat. That is, the sum of all the omegas should equal to 1. And it also predicts how galaxies should look on all scales larger than about 30 million light years. So I was sort of brought up at the end of this. All happened before I entered graduate school. And I have to admit, I always thought inflation looked a little flaky to me. Seemed to me like a cartoon. Cold dark matter, well, we're inventing something we couldn't see. When you're allowed to invent things, you can predict almost anything. And so when I was in the beginning of graduate school in 1990, everyone assumed that the universe was made up of gravitating matter, matter that has gravity like Newton thought it would. And the theorist view of the world was that the universe started with inflation, and you had cold dark matter, which predicted what the universe was, and this meant that the omega, that is, the universe was flat, but this also implied to get things to be old enough by the age that the Hubble constant had to have a value less than 50 kilometers per second per megaparsec, and that the observers were simply wrong when they went out and measured omega matter. We went out and measured omega matter, and we typically got values about 0.2 or 0.3. And we measured Hubble constant, and we typically got values, like my thesis, of about 70. So the observers, which I was trained at, said we go out and we measure omega matter, we get 0.2. We get Hubble constant, which was maybe down to 50, but not likely. And we simply just had to say that inflation and cold dark matter were wrong. So, of course, you want to go out and test these things. And the first thing that was looked at was the large-scale structure of the universe. And when people went out and looked essentially at how galaxies were correlated with each other compared to random, so in this diagram, this is a logarithmic scale, and 0 means it's completely random, and as you go up, you have a higher probability of galaxies being closer to each other, to be associated with each other on different scales on the sky. And if you go through and use the model of cold dark matter plus inflation, you got a curve which disagreed with the data of what was seen on the sky. There was more structure on the largest scales across the sky than could be explained with the model, unless you did one of a couple things. You could add a cosmological constant. That's one way to fix this problem. Or you could make the Hubble constant very, very low, down to 30 kilometers per second per megaparsec. All right? So what did people do at the time? So one group, for example, this paper said maybe there's a cosmological constant, but the same people, a year later, essentially say here that the value of cosmological constant needed to work these miracles, that is, to fix this problem of large-scale structure, is extraordinarily small, 10 to the 120 times smaller than its natural value. Okay? Well, probably not going to talk too much about the natural value, but it didn't make sense from particle physics. Such fine-tuning seems sufficiently unattractive that most cosmologists regard this solution as a long shot. And this paper was largely ignored because people just thought it was crazy. Other people went through and said, maybe the Hubble constant is 30. After this paper, myself and a colleague with Joe Silk said, if you're willing to go through and waste pay charges on papers like this, you should be willing to bet a case of scotch on the value of the Hubble constant. So we made a bet in 1995 with Joe Silk about the value of the Hubble constant. And we said if the Hubble constant's less than 50, we'll give you a case of scotch. If it's greater than 50, you give us a case of scotch. And you got to pay up, and we'll have to pay up by the end of the millennium and at the end of 2000. So Joe Silk said, no, I don't want to go 50. How about 70? And I said, I think the Hubble constant is 70, so I'm not going to bet at 70. So he eventually talked us down to 60. So finally we said, okay, we'll take the bet at 60. So 2001 came to fruition, and we said, okay, the Hubble constant's clearly 70. Please give us our money, our scotch. And unfortunately, the person we had adjudicate this was Jim Peebles. And Jim Peebles said, well, I agree the Hubble constant looks like it's 70, but it's not to 4 standard deviations of significance, so there is no winner. But I have Joe Silk in 1994, or in 2000, with a thing saying, up on a screen saying the Hubble constant's 70, plus or minus 5. So I even had evidence from him that it was 70, and I still didn't win this bet. Oh well. Other people said in 1995, hey, the cosmological constant is back, but in all these papers, there's a common theme, and there's several like this. They're written by theorists who say inflation is correct, and if inflation is correct and cold dark matter is correct, you need a cosmological constant. I, as an observer, said, why should I believe these two things? I mean, they hadn't given us much at the time. The only paper that I think gets a lot, I give a lot of credit to, is this one, also in 1995, which still made the same assertion of cold dark matter and inflation being correct. But they actually measured, and I say measured, using this diagram from the earliest results of the cosmic microwave background, that the universe seemed to be near flat. And when you made the universe flat, it was very difficult to have anything other than a cosmological constant be correct, as I'll show you. The approach we took is we said, let's make that measurement of distance back in time, and we were studying type 1a supernovae, where we could go through and measure, use these things as essentially standard light bulbs. We could calibrate how many watts they put out, and that enabled us to measure distances, it turned out, quite accurately back across the cosmos. These things are so bright, they're 5 billion times brighter than our sun, that we could see them easily 8 or 9, well not easily, with a lot of difficulty we could see them 8 or 9 billion years into the past. So we could really expand, make our measurements across a large part of the universe's life. So type 1a supernova is an explosion, a thermonuclear detonation of a white dwarf star. A white dwarf star is the remnant of our sun. When it finishes burning off all of its hydrogen and then helium, it will collapse down to an electron degenerate ball of gas. So the degeneracy pressure of electrons keeps this thing from falling into gravity. And Chandrasekhar showed that this degeneracy pressure will be overcome by gravity when this star is about 1.38 times the mass of the sun. So imagine somehow you add material to this and you make it exceed the Chandrasekhar mass. Then what happens? Well, you end up with the whole thing burning like a giant nuclear bomb. And so I'll just quickly, you start the thing exploding, you make 56 nickel. 56 nickel is radioactive, the gamma rays go out, diffuse their energy, and the whole thing expands at about 10% of the speed of light and gets incredibly bright. So they're a very nice little tool we have. But do they really work? Well, the high redshift type 1a supernova history is long. Fritz Zwicky, who did a lot of pioneering work in astronomy, did the first search for supernovae using a Schmidt telescope, not named after any of my relatives, but a one-armed optician who blew his other arm off playing with dynamite when he was young. And he used that telescope from the 1930s to 1960s to discover most of the supernovae that were around during that period. And this eventually led to the first Hubble diagram, that is, distance versus redshift, in 1968. It turned out these type 1a supernovae, which are the explosions of stars without hydrogen in their spectrum, had a contaminant. They had a contaminant caused by massive stars, which explode by a completely different mechanism of what we call core collapse, where the gravitational energy of the star collapsing down not to an electron degenerate star, but a neutron degenerate star, that energy, a gravitational energy, creates a shock wave which travels out and disrupts the star. Some of these stars, a lot of these stars will have a big envelope of hydrogen on the outside, but some of them are able to shed that hydrogen envelope and explode with no hydrogen. They look surprisingly similar to the type 1a thermonuclear detonations. And so similar, it wasn't until 1984 and 1985 that this contamination was realized. We're pretty good at spotting it now, but probably not absolutely perfect. But I think the really big things started happening when the technology came, which allowed us to look to very large distances. The first distance supernova was discovered in 1988 by a Danish team. It was at a redshift of 0.3, so that's about 1.5 billion years in the past. They spent 2 years looking for this single object, and when they discovered it, they hadn't found it early enough to actually use it to measure a distance. So they gave up. The problem was that they had really gone a little early. They had gone before the technology was ready for them. At the same time, a group at Berkeley, which was eventually led by Saul Perlmutter, started at the same time. And in 1994, after 5 hard years of work, the technology was there, and they were able to find 7 supernovae at approximately a redshift of 0.4 in a few months. At the same time that I found out about these discoveries, my colleagues in Chile, which I'll talk about in just a second, went through and took really good data of 29 nearby type 1a supernovae so that you could actually see how good you could use these to measure distances. So those two things came together, and I'll just highlight the work of the Calan Tololo group. And when they took that, they found that type 1a supernovae are not perfect. They're not all the same. There's a little bit of a difference. The objects which rise and fall quickly are fainter than the ones that rise and fall slowly. And we can understand this. These objects produce very little nickel-56 compared to these objects. And if you go through and do the theoretical calculations, this more or less makes sense. But when you use a type 1a supernova, this is where astronomy and physics differs. Astronomers are the pack rats of the physics world. We can't go out and design an experiment and then go do it. We have to give what nature gives us. And so what we do is we use these things as our tools, but of course we are not completely in control of them. So we go through and use these things and we see how well we do. And when we do it, we get a diagram of redshift in the nearby universe versus distance. So this is a logarithmic distance this way. And I should say that there's about 120 objects in this set. And redshift, its first order in the nearby universe, is a perfect surrogate for distance. That is, redshift and distance really match up no matter what the universe has. It's linear. What's in the universe makes almost no effect to the universe. And these data show that we can measure distances with these supernovae to about 7% per object. Now, 7% per object to an astronomer is pretty good. To a physicist, it sounds pretty bad. Okay? But again, we use what we can. So we started our team in 1994, and this was a team I was allowed to start with my colleagues when I was 27 years old, and I give them a lot of credit that they allowed someone who was 27 years old and fresh-faced out of graduate school to go through and essentially take charge of a project. And it was a great honor they bestowed on me, and I certainly am grateful because I think many groups would not have allowed that to happen. At the same time, Saul Perlmutter was leading a group that was out of Berkeley, and both of our groups included people around the world. And so here's Saul and me in a picture taken in Aspen. And our teams were well known in the mid-1990s for not getting along very well. I always get along with Saul, but many of my team members did not get along so well with their team members. And there were lots of embarrassing fights which continue today. And I apologize. I avoid the fights. So anyway, the most embarrassing part about this picture is I actually think Saul looks like he's about to deck me. I don't seem to know what I'm doing there. So when we go out, we observe the sky. We watch the stars go by. We sip our Chardonnay or Rioja, depending on where we're doing, and take data with the Ceratololo, in this case, 4 meter. But in fact, it's not such an easy lifestyle. This is Saurabh Jha, and he's doing something. He's looking for supernovae. He was a graduate student when this picture was taken. This is Peter Garnovich. He was an assistant professor, and he's looking for supernovae. This is John Tonry, a full professor. He's looking for supernovae. And of course, I was wandering around taking pictures. But why is this so difficult? Well, each image we were taking, 8,000 by 8,000 pixels, covered over the area of the moon. I'm going to show you one image, that one, blown up here. And so there are 5,000 galaxies on this one picture, which is 1/8 of one image that we were taking every 2 minutes. Okay? This is 1995, where we had, 100 megahertz computers with 2 to 5 gigabyte hard drives, and we were taking 50 gigabytes of data a night. The ability to find these things in 1995 is the most difficult thing I have ever had to do in my scientific career. And the idea is we had to find the exploding star in this diagram. Here it is. And it's not just because there is a star next to a galaxy. We actually take 2 images. And what we would do is digitally align these images and then match them in intensity and the shape of the stars, subtract them, and have the computer sift through that so that we could then go through and say nothing had become something in these 3 weeks. So this supernova, which is, as I say, about 5 billion times brighter than our own sun, is almost 5 billion light years in distance. So we are looking back before the time the Earth was formed with one of these objects. So in 1998, ourselves, shown here at the Gruber Prize, the team, announced an accelerating universe. And to our surprise, at the same time, the other team found the same result. So when we started getting this data, and I'll just show you the data, these are nearby objects taken in Chile, and these are the objects at high redshift, and there's a fair bit of scatter, but on average, the objects lie above the line. Now, the 2 teams had slightly different ways of doing things. We had fewer objects, but each one had better precision. They had more objects of less precision, and we had observed all the nearby objects. Okay? So the teams, though, did get the same answer, essentially indistinguishable, as I'll show you the formal error contours. And people took note because it was the first thing that our 2 teams had ever agreed on in public. Doesn't mean we're right, but this essentially shows you the confidence intervals of measuring the cosmological constant and omega matter. Each of us had about a 3 standard deviation measurement that there must be a cosmological constant. Put together, it was about 4.5 standard deviations. All right. So our high redshift supernova observations directly measured distances which were incompatible with any universes that only had normal matter. But of course, the supernovae themselves, we didn't understand that well, and they could be been affected by dust, evolution, or measurement difficulties in some way we hadn't corrected. And so I think the community felt they were not to be completely trusted on their own. Nonetheless, there seemed to be enough excitement that there was, there was sort of a panacea for cosmology, because the cosmological constant fixed all the problems that remained in cosmology in 1998. The only thing it contradicted was a single measurement of trying to figure out how much cosmological constant there could be by the number of gravitational lenses that we saw in the universe. That measurement has been shown to have had some mistakes in it, and so it's no longer applicable. But that was the only thing it went against at the time. I think because both teams got the answer so quickly, we received a fair bit of attention very early on, probably more than we deserved. So people often ask whether or not, I was really, had a eureka moment where I suddenly realized the universe was accelerating. The answer is no. Adam Rees was doing a lot of the data reduction for this part of the project, and he called me up once in the middle of the night and told me that the universe seemed to be doing something unexpected, and I just assumed, as did he, that we had made a mistake somewhere. And it took us months to slowly convince ourselves that no, we hadn't actually made a mistake. The universe really did seem to be speeding up. All right, so what are the other observations that came along? The first was of the cosmic microwave background. And in this diagram, you're looking at essentially the scale of fluctuation. So this is more or less a Fourier transform. It turns out it's a spherical harmonic, but it's effectively, you have an amplitude of fluctuation on the sky, and different models give you different views of what those fluctuations should look like. And so by 1998, this was what the observations looked like, and if you absolutely believed this, this showed that the universe was effectively flat. But it wasn't really until 2000 that the measurements got really good with two experiments, Boomerang and Maxima, that clearly showed the first wiggle, which we call the Doppler peak, was at a place which only made sense if the universe were flat. So putting all these things together on this diagram, we had the supernova here, and then we had the cosmic microwave background here, and when you added them together, you got essentially the canonical value. 30% of the universe was gravitating matter, and 70% was a cosmological constant. In addition, at this time, the first very large redshift survey, 200,000 galaxies came out, and they were able to weigh the universe by looking at how matter fell onto itself in the redshift survey. Essentially, they compared distances this way on the sky compared to distances this way on the sky, which were redshifts. So they compared the redshift, which was affected by gravity, to this distance on the sky, which is independent of gravity. And by that causes a squishing. This is redshift this way, this is on the sky, and that squishing weighs the universe, and they found very conclusively that the amount of density in the universe was about 30%. And so we found ourselves very quickly that in order for the dark energy to go away, it required two of these three experiments to be wrong. Here are the supernovae, here was the cosmic microwave background, here was the large-scale structure, and they all overlapped at a single spot, right here, right where we're still at today. All right, so progress went quickly. WMAP made an exquisite measurement of the cosmic microwave background. We got better supernovae, there were more redshifts made, the Hubble constant was measured more accurately. And so by 2003, we had not just started worrying about the cosmological constant, we started worrying about its equation of state. Is the stuff that's pushing on the universe the cosmological constant, or is it something else? And by then, we had already been able to see that the whatever was pushing on the universe was very close, had an equation of state very close to -1, and was certainly consistent with Einstein's version of a cosmological constant. Now, to give a little bit of perspective as I get to the end, a new type of measurement has become very important in the last few years. These are called baryon acoustic oscillations. That first bump in the cosmic microwave background here is essentially a pressure wave in the early universe where matter fell in and stopped as pressure pushed out on the infalling matter as it heated up. And so that is a scale in the universe that was frozen out because the universe was, had the photons and matter coupled because the universe was ionized, and photons were scattering from electron to electron. And then suddenly the universe became transparent when it recombined, and so the photons and the matter were no longer coupled, and so this acoustic pressure wave was frozen in space as the universe suddenly became transparent. And so this scale in the universe we can calculate from physics to be 147 megaparsecs, to about 1% from the cosmic microwave background. In the modern day, it should be 147 megaparsecs, and we can measure that scale today in the distribution of galaxies. So this is essentially the power spectrum of the distribution of galaxies as a function of redshift, and there you can see, measured by Eisenstein in 2005, this bump. This bump is that bump, and that allows you to measure a distance a long time ago compared to nearby, and that is essentially the way we're going to, in the future, probably measure the size of the universe back in time. The beautiful thing of this measurement is we understand the physics really, really well, and the measurement is really, really boring, but very, very easy. All that you do is you go out with the largest telescope you can find and look at hundreds of thousands of test particles, which are galaxies. You measure their redshift, you measure their position on the sky, and that allows you to measure the power spectrum, and you look for this bump, and you figure out how big it is and what redshift it is, and you compare it to the cosmic microwave background, and that is a series of distance measurements, not of how bright something is, but how big something appears on the sky. All right? And that allows you to measure, in the same way supernovae do, the cosmological parameters. The difficulty is, right now it takes about 5 years to do one of these experiments, and they have less precision by an order of magnitude than the supernovae. But the plans are to spend $1 billion, use a spacecraft, and do maybe 10 million test particles over a huge volume, and then they become much better than the supernovae, and it's hoped they have smaller systematic effects. So where are the supernovae now? Well, we've been busy, and we have measured thousands of objects now, and I actually don't show all of them on this diagram, but at this point, when we put everything together, we get the following diagrams. Cosmic microwave background, here's the baryon acoustic oscillations, the supernovae, and our error bars are becoming very, very precise. If you look at what the equation of state of the universe would be, it's within 10% of a cosmological constant. We can even go through and measure things like the curvature of the universe very accurately, along with everything else. We can measure all of these things simultaneously, and what we're finding is the universe looks flat and full of something that looks an awful lot like the cosmological constant. We can even go one step further. The data are so good now, we can get rid of general relativity. Because some people say maybe general relativity is wrong. We can use the pure geometry. We can use the Robertson-Walker metric and measure whether or not the universe is expanding. So this is the acceleration of the universe. And when you do this, not using general relativity, only assuming that the universe is homogeneous and isotropic, we clearly see the signature of acceleration looking back to a redshift of about 0.5 to 0.6. So the accelerating universe is with us, independent of general relativity. So is there any way out of dark energy? I'm not sure what you would do if you ever came to this stop sign, but I think the answer is almost not. The only way I can see dark energy going away, the accelerating universe going away, is if the universe is not homogeneous or isotropic. Now, some people would like to have, it turns out you could make us be in the whole of the universe. You could make us be in a void in the universe where there's just not as many galaxies around the Milky Way compared to the rest of the universe. And you can tune how many galaxies there are to perfectly reproduce the observations. You're allowed to do that. But of course, we have to be within 1% of the center of that void, and we have to have the void fall off just perfectly in density to match the observations. And that seems even crazier than the model we have of a cosmological constant. There also, I should say, is some discussion whether or not the growth of structure will violate the idea of the Robertson-Walker metric. 95% of the people in the world I trust say this is not a problem, but 5% of the people in the world I trust say it is. So this is very controversial. It's probably not an issue, but enough people think it might be that I think you have to worry about it. So I'm going to skip ahead here just a bit. The big question we have is, what is dark energy? So it could be Einstein's version of general relativity. But another possibility is something that's known as quintessence. So I was walking around Tokyo, and I found this sign, and this says Quintessence Hair and Makeup Gallery. And it made me ask the question, is quintessence cosmology or cosmetology? So cosmetology is the English word for when you go and get your hair cut. So quintessence is a way of saying the same thing that created inflation, a scalar field, part of supersymmetry, some supersymmetry type particle, is responsible for the acceleration now. So we can try to test this, but these are toy models. They can do anything we can observe right now. There are no constraints on them, so no matter what observation I make, these guys will be able to fit it right now. So I'm not sure if that's a compelling thing to chase when they can fit any observation I make. The other option is maybe Einstein is wrong, and somehow the gravity in the universe leads to acceleration without dark energy. But you would have to have the gravity actually induce acceleration over time. It's certainly an important problem, and there are lots of ideas. This is a couple months in AstroPH of all the different solutions to dark energy. Our papers get a lot of citations because theorists produce any number of ideas to describe dark energy. And you have all sorts of interesting things here, many of which I do not understand. None have any particular merit compared to any other ones. So observationally, dark energy looks a lot like the cosmological constant. We cannot find any fault with Einstein's version. All right? And so, unfortunately, because there is no real theoretical guidance, there's nothing to test, observers are essentially searching blindly, hoping to find something in the observations that say it isn't the cosmological constant. We don't know what, but that's what we're doing because that's what the theorists are saying we should do. We don't understand what's going on. So are there any indications of that? Well, there's one measurement I'll show you, is that if you do the Baryon acoustic oscillations at the nearest part of the universe, they disagree slightly with the canonical supernova-driven model. The difference is less than 2 standard deviations. We're getting more data, but it's very difficult to make measurements because there's just not enough galaxies in the sky to make a measurement here. You've got to go to higher redshift. So where are we going? Well, here's the latest supernova data. The supernova data have come grinding to a halt because we've gotten to the point where we have enough supernovae that the statistical precision, if we just drew a line in here, has systematic errors we do not understand anymore. We've gotten to the point where we have broke type 1a supernovae. We can use them, it seems, to about 2% or 1.5% in measuring distances, but depending on who uses them now, we get different answers at about the 1.5% measure, 1.5% level, depending on the assumptions we make. And we're scratching our head, we're trying to understand why, what's causing these problems, but as of yet, we do not have an answer. And so supernovae still, by far and away, provide the strictest measurements of the acceleration and the cosmology, but I'm not convinced we're going to do much better. Other things, such as the cosmic microwave background, don't do much. There's these huge baryon acoustic oscillation surveys, which are, as I said, literally 600 million. There's Euclid is a European mission that's at least that amount. There's something called JDAM, which is about $1 billion in the US. The square kilometer ray might do this. It's probably the best way of the future, but I'm not overly optimistic. In my conclusion, I will note that I actually think dark energy, if it is going to be solved in my lifetime, is going to be solved by the unexpected, by an act of brilliance of a theorist, or by people such as myself and others going out and trying to understand the mysteries of the universe, doing things other than dark energy, exploring the universe from the solar system level to 13.7 billion years ago, and suddenly gaining an insight from some unexpected place, whether it be the fine structure constant varying, or probes going out of the solar system not quite behaving like Newtonian gravity. I don't know, but that would be my guess is our best bet for the future of discovering dark energy. Thank you very much.